Non-local quantum events by Dave Marsland of Cardiff Theosophical Society. The study of non-local quantum events is a fascinating and complex area of physics that has intrigued scientists and philosophers for decades. These events, which defy classical notions of locality and causality, are at the heart of the mysterious and counterintuitive nature of quantum mechanics. Non-locality in the context of quantum physics refers to the phenomenon where particles can be instantaneously connected or correlated with each other regardless of the distance separating them. This means that the behaviour of one particle can be influenced by the state of another particle even if they are light years apart. Non-locality challenges our traditional understanding of cause and effect, suggesting that there may be connections between particles that transcend our conventional notions of space and time. The concept of non-locality in quantum physics can be traced back to the early 20th century with the development of quantum mechanics. One of the key figures in this development was Albert Einstein, who along with Boris Podolsky and Nathan Rosen proposed the famous EPR paradox in 1935. The EPR paradox highlighted the potential for non-locality in quantum mechanics by considering the correlations between distant particles, which seem to imply instantaneous action at a distance, in apparent conflict with the principles of relativity. The EPR paradox spurred intense debate and theoretical investigations, leading to the formation of Bell's theorem in the 1960s by physicist John Bell. Bell's theorem provided a mathematical framework for testing the existence of non-local correlations in quantum systems, and it gave rise to a series of experiments aimed at probing the nature of quantum entanglement and non-locality. Bell's theorem states that if certain predictions of quantum theory are correct, our world is non-local. Non-local here means that there are interactions between events that are too far apart in space and too close in time for the events themselves to be linked by signals moving at the speed of light. At the heart of non-local quantum events lies the phenomenon of quantum entanglement. Entanglement occurs when two or more particles become correlated in such a way that the state of one particle is intimately related to the state of another, regardless of the distance between them. This correlation persists even when the particles are separated by vast distances, leading for the potential for non-local effects. In the framework of quantum mechanics, the state of a system is described by a wave function which encodes the probabilities of different outcomes when the system is measured. When two particles are entangled, their individual wave functions become interdependent, and measurements on one particle can instantaneously affect the state of the other, even if they are separated by large distances. The phenomenon of quantum entanglement has been thoroughly studied and verified through numerous experiments, confirming its existence and its non-local nature. The theoretical foundations of non-local quantum events are thus firmly grounded in the framework of quantum mechanics, which provides a formalism for understanding and describing the non-local correlations between entangled particles. Experimental investigations of non-local quantum events have been a central focus of research in quantum physics. Over the past several decades, a series of landmark experiments have been conducted to test the predictions of quantum mechanics regarding non-locality and entanglement. One of the most famous experiments demonstrating non-local quantum effects is the Aspect experiment, conducted by Alain Aspect and his collaborators in the 1980s. In this experiment, entangled pairs of particles were created and separated by large distances, and measurements on one particle were shown to instantaneously affect the state of the other in a manner consistent with non-local correlations predicted by quantum mechanics. Subsequent experiments have further confirmed the reality of non-local quantum events, ruling out various alternative explanations and loopholes that could potentially undermine the non-local interpretation of quantum entanglement. These experiments have provided compelling evidence for the existence of non-local correlations in quantum systems, solidifying the empirical foundation of non-local quantum events. The existence of non-local quantum events has profound implications for our understanding of the nature of reality and the fundamental principles of physics. The non-locality of quantum entanglement challenges classical notions of locality and causality, raising deep questions about the nature of space, time, and the interconnectedness of physical systems. One interpretation of non-local quantum events is that they suggest a fundamental breakdown of classical concepts of separability and locality, pointing towards a more holistic and interconnected view of the quantum world. This has led to philosophical debates about the nature of reality and the implications of non-locality for our understanding of the fabric of the universe. Furthermore, the potential for non-local quantum effects has practical implications for quantum technologies such as quantum communication and quantum computing. The phenomenon of quantum entanglement, with its non-local correlations, forms the basis for quantum cryptography and quantum teleportation, enabling secure communication and novel information processing protocols that harness the non-local nature of quantum systems. In conclusion, the study of non-local quantum events represents a fascinating and profound frontier in physics, with deep implications for our understanding of the quantum world and its connection to the broader fabric of reality. Through historical, theoretical, and experimental investigations, scientists have uncovered the non-local nature of quantum entanglement, challenging classical notions of locality and causality and opening new avenues for technological and philosophical exploration. The continued study of non-local quantum events promises to shed light on the fundamental nature of the quantum realm and its implications for our understanding of the universe.